Today we're going to take a look at some applications of linear programming duality. So duality is somewhat of a strange concept. When you see it for the first time, you might wonder, is that good for anything? And it's good for lots of things, and some examples are what we're going to take a look at today, beginning with maximum matching. So what's a matching? We have a graph. A matching is a set of edges such that no vertex is incident to two edges, or no two edges share the same vertex. So this is a matching here, and we are now interested in matchings that are as large as possible. And there are two concepts there. There's maximal matching. So a matching is maximal if we cannot add edges to that matching. So this is a maximal matching. But what we're interested in today are maximum matching. So those are matchings that are as large as possible. So this is a maximal matching, but is it also maximum? It is not, because we have three edges here. It's not possible to simply add an edge, but if we would have picked those four edges, those are also a matching, and this one indeed is maximum. Yeah, so not every matching can be extended to a maximum one, or stated differently, not every maximum matching is maximum. Now, typical example of matchings, we have jobs, we have people, we want to assign those. So let's take this one here. So here we have the workers in a company, and here we have jobs that they would be willing to take. So an edge says Amos would be willing to be the representative. And now the question, if we ask about perfect matchings, is can we find a job for every person and for every person a job? So can we find a matching such that every job occurs exactly once, every person also? Is that the case here? It is not. So why not? For that, we can look at the neighborhoods of vertices, sets of vertices. So if you look at this set of vertices here, we have 1, 2, 3, 4, 5 vertices. Its neighborhood are the vertices that share an edge with one of those, and that is this set here. And this neighborhood is smaller than the set itself. And this then means that I will not be able to, for every job here, find a person. Also, I have 5 jobs, 4 people, that cannot work. This can actually be made stronger, so an equivalence. So that's Hall's theorem. If we have a bipartite graph with two sets x and y, and only edges between x and y, then G has a matching covering of x. So meaning there is a matching such that every vertex of x is included. If and only if, for any neighborhood of some subset of x, the number of vertices in that neighborhood is at least as large as the set itself. So we've seen an example that if the neighborhood is too small, then this cannot work. But this is now also the other direction. So if we have for every neighborhood enough vertices, then we can actually get a matching. So here, if I have this on the one side for x, and not for the other side, then also for y, then I'm actually asking for perfect matchings. So this is Hall's theorem. And so if we have a matching covering, then of course the neighborhoods are large enough. That we've already also seen by the example that if the neighborhoods are not large enough, obviously we cannot have a matching. So one direction is clear, the other direction is more work. And the other direction we're going to prove using König's theorem. König's theorem states the following: in any bipartite graph, the size of the minimum vertex cover equals the size of the maximum matching. So first of all, what does vertex cover mean? Vertex cover means, so a subset of the vertices is a vertex cover if for every edge at least one of the endpoints is in the cover, which is the case in this example here. So for this edge here, for instance, this one. And if I look at the smallest such vertex cover, its size is exactly the size of the largest matching in that graph. This holds for bipartite graphs. And if you have a minimum here and a maximum there, that gives you a strong indication that we're going to prove this with duality. But before proving König's theorem, we're going to show how, if we have König's theorem, how Hall's theorem follows. So back to Hall's theorem, we have a bipartite graph, and what we need to prove is that if the neighborhoods are large enough, so if for every x subset of x I have that its neighborhood is at least its size, that we then actually also can find a matching covering of x. So a matching that includes all the vertices of x. And we're going to show this using König's theorem. So what we're saying here is that there is a matching of size of x, and that then actually is also a maximum matching, because I will not be able to have more edges than I have edges here. And instead of showing that there's such a matching of size x, we show that any vertex cover has size at least x, because if every vertex cover has size at least x, also the minimum vertex cover has size at least x. And that then means, by König's theorem, that then the maximum matching also has at least that size. So all of the vertices in x are covered. So now we need to show that no matter which vertex cover I take, it has size at least x, and we're going to prove that by contradiction. We're going to assume there is a smaller vertex cover with fewer than size of x vertices. So the blue vertices here, those indicate such a vertex cover. And on the one side there will be, so this is just I will just call the number of vertices on the side in x that are also in this cover, and that number I will call k. And then on the other side, so this in my case is just this vertex, the size of the remaining vertices in the cover is x smaller than x minus k, because I said my cover has fewer than x vertices. So if on the one side I have k, then on the other I have fewer than x minus k. It has to add up to something smaller than x. Now I'm going to look at the following. I'm going to look at the vertices in x that are not included in the cover. Since I have k vertices in the cover, the size of x without those vertices, this set has size x minus k. Now I'm going to take the neighborhood of this set, which will be somewhere here, not all of those, but I know it has size at least x minus k. So these vertices here have a neighborhood on the other side, let's say those purple ones, in my example actually all vertices, and because we have this condition, the size of that is at least the size of the set over here, so at least x minus k. But that now means that not all of those vertices, so in my case those purple vertices, not all of them can be in C, because C on that side only has less than x minus k vertices. But that means there is a vertex that is in the neighborhood of the not covered vertices of x, which is also not within the cover in y. So for instance, this one down here. It's not, both endpoints are not in C. But that means that edge is not covered, and that is a contradiction because we started with a vertex cover. So we know every vertex cover has size at least x, and therefore the minimum vertex cover has size at least x, the maximum matching has size at least x, or actually it has to be simply x, but it means that everything is covered. This proves Hall's theorem. We still need to prove König's theorem, but before doing so, we need another tool, and that is total unimodular matrices. So a matrix is totally unimodular if any submatrix has a determinant which is either 0, 1, or -1. So an example of this is this matrix here. This is totally unimodular. Pick any submatrix. Let me pick small ones. So this one has a determinant of, okay, this product minus that product is simply 0. I'll also find ones like this. We have this minus that is 1. And I could also get -1. And if I take larger submatrices, so square submatrices like this one, then yeah, I would need to calculate so I get this times the determinant of that one here. This is 1, -1, so -1 plus, and this times that -1, this is 0. So again, -1. So this is a totally unimodular matrix. We'll actually prove that it is the case, but for this class of vertices of matrices, because this is actually a matrix with some meaning. So do you recognize what kind of matrix this is? This matrix corresponds to an incidence matrix of a directed graph. So here is a directed graph, and we have for a row for every vertex, a column for every edge. And now let's look at the edge E1. This goes from V1, so they have a -1, to V2, there I have a 1. So this is the incidence matrix of a directed graph. We will show that this is totally unimodular sooner or later, but for now, we just want to have the concept. If a matrix is totally unimodular, then the entries have to be 0, -1, or 1. Why is that the case? Yeah, I mean, because one entry as such is also a submatrix. But it's not sufficient. So having 0, -1, and 1 as entries is not sufficient to be totally unimodular. So this one, for instance, has a determinant of 1 minus -1, so 2. One specific way of getting total unimodular matrices that we're going to use later is the following. If A is totally unimodular, then if I add a vector of zeros, which is 1, 1 somewhere, to it, then it remains totally unimodular. So this is now as a column, or likewise, if I add an extra row of this form, then that is also the case. Why are we interested in totally unimodular matrices? Because of the following theorem. So if we have a linear program in this form, maximize C transpose X, subject to A, X smaller equal B with non-negative variables, but what I'm going to show you also holds for other variants of linear programs, then if A is totally unimodular and B is integer, then if there is an optimal solution, there is also an integral optimal solution. What that means is, imagine I have an integer linear program which fulfills the condition that A is totally unimodular and B is integer. And then if I relax that program and solve the relaxed LP, then that relaxed LP has also an optimal integral solution. So I'm actually already solving my ILP. Of course, there could also be other solutions, but as we will see, if we use, for instance, the simplex method, it will actually give us an integral solution to this problem. Yeah, so this is very useful. If we have this property, then the ILP is easy to solve, or can be simply solved by solving a linear program. Let's prove this, and we prove this constructively by applying the simplex method. For that, we will first need to bring our linear program into equation form. So we add slack variables. Now we have a bar x bar equals b instead of smaller equal b. And this is now the matrix A, and then a matrix with 1s on the diagonal, 0 below and above. So this is for the slack variables. And I get m additional variables, the slack variables, in this linear program. Now I'm going to solve this using the simplex method. So we're going to find an optimal basic feasible solution. Let's call it x star bar, corresponding to some basis. For the solution, we have the following. So this is simply a property of the simplex method. You might want to watch the video on the simplex method if this doesn't seem familiar. or simply believe it. So I get that the x bar star restricted to the basis, to the variables in the basis, equals the a bar. Now I just take the columns corresponding to the basis to the -1 times b. Now we have that a bar is totally unimodular and it's also non-singular. So what that means is that, so because it's totally unimodular, we know that the determinant of a bar b is either -1, 0, or 1, because unimodular means for any square submatrix, I get that this is a square submatrix. From the non-singularity, we get that the determinant is non-zero. So 0 goes away. I only have the options -1 and 1. And now we use Cramer's rule, which you might still know from your linear algebra class. Otherwise, I'm going to tell it to you now. So, or at least how we're going to use it. Cramer's rule tells us something about the coefficients of the solution, based on knowing that it is this here. So this can be expressed in terms of certain determinants, and in particular in the solution, in the denominator, we have the determinant of a, b. And because we know that this determinant is either -1 or 1, we know that the x, the variables are actually integers. So generally they would be rationals, but with a denominator which is either -1 or 1, and a rational where the denominator, or a fraction where the denominator is 1 or -1, that is also simply an integer. So we know that we get the variables x star for the basis are all integers. For the non-basic variables, it's 0. So overall, I get an integer solution. To prove König's theorem, we need one more lemma, and that is the following. Namely, we want to show that what we just learned, we can apply in the setting. And for that, what we want to show that the incidence matrix of a bipartite graph is totally unimodular. Yeah, so here I have a bipartite graph. Here's a corresponding incidence matrix. So there's E1 here. If I look at the column, there's exactly 2 entries that are 1. So what we need to prove is that no matter which submatrix we take, its determinant is either 0, 1, or -1. So for submatrices, and we do this by induction. So for submatrices of size 1, that's clear, because for size 1, it's either 0 or 1. Now let's assume it's true for L-1. Now we want to show it for matrices, or for submatrices of size L by L. And we make the following case distinction. So if in this submatrix there is, so let me pick a submatrix, this one. So if in this submatrix there is a column which only contains zeros, like this column here, then I know the determinant is 0, so I'm done. If in the submatrix there is a column which contains only 1, 1, like this one here, also the other two actually, then by expanding using that column, I can express the determinant of the submatrix as, in this case, 1 and then some sign, so so either 1 or -1 times the submatrix of smaller size, and then I can apply an induction, get 1, -1, or 0 for that submatrix. So overall, I get 1, -1, or 0. So now the final and interesting case is that we have for every column of the submatrix 2 ones. But now we're going to do the following. I will partition the rows of this submatrix Q according to whether the corresponding vertex is either in X or in Y. So I have, for instance, so let's say I take the whole matrix, then v1, v2, and v3 are on the one side, and v4 and v5 on the other. If I partition like that, now if you look at the sum of those top rows, then in every column I will have a 1, because I know for each of the columns there were 2 1s, and 1 1 will be will correspond to a vector vertex in x, 1 to a vertex in y. So if I partition like that, I have 1 1 for each of the columns in one of those rows, but likewise down here. So if I sum up the rows corresponding to x, I get an all 1 vector. If I sum up the rows corresponding to y, I get an all 1 vector. But this means that these rows are linearly dependent, and therefore the determinant is 0, which proves the lemma. Now we're ready to prove König's theorem. So what was König's theorem again? In a bipartite graph, the size of the minimum vertex cover is equal to the size of the maximum matching. Let's illustrate that first. So here I have 2 copies of the same graph. Now in the top version you see the minimum vertex cover. It has size 1, 2, 3, 4, 5, 6. In the lower one you see a maximum matching 1, 2, 3, 4, 5, 6. And these are indeed equal in size, and we're going to see that this holds in general. For this we're going to use LP duality. So let A be the incidence matrix of our bipartite graph. Now how do the linear programs look like? So if you start with the minimum vertex cover, there I will have, okay, we want to minimize. I have a variable for each vertex. I want to minimize the sum of vertices selected. So here I minimize. I have a variable per vertex. I want to minimize the sum of vertices selected. I will have for every edge a constraint saying for that edge at least one of the vertices needs to be selected. Now if you take A transposed here and times y, what does that mean? It means that if I look at a certain row of this matrix, so A was the incidence matrix. So in the incidence matrix we had rows corresponding to, so A is of the type where I have here the vertices and here the edges, and a 1 says that vertex occurs in that edge. Now if I transpose it, I have here the edges and here the vertices, and I have ones in a row. I have the ones where for the vertices that are in that edge. Now in this formulation here, A transpose y, the rows, so if I look at this at the various constraint, a constraint corresponds to a row here, and it picks up, so for a certain edge it picks up exactly the 2 vertices incident to that edge. I want to have that one of them is selected, so I'm saying that this has to be larger equal 1 for each of the rows. So this is not a single one, this is a 1 vector of ones. B is a vector of 1. And all of the variables should be non-negative. This is the covering program. In the matching we so this is now, as we can actually read off, this is dual to the minimum vertex cover one, because the ones here show up as the coefficients here. The ones here show up as the ones here. And A transposed gives me an A here. Larger equal here gives me that these have to be larger equal, and the larger equal here gives me a smaller equal there. So this is a dual program, and it corresponds exactly to the maximum matching problem, because we want to select. So here we had for every constraint, for every edge a constraint. In the dual we have for every primal constraint a variable. So we have a variable for every edge. We want to maximize the number of edges selected, constraint to that, and now I have for every primal variable, so for every vertex here I have a constraint on the right hand side saying that this vertex should only have at most one incident edge. Yeah, so now we again back in the setting of A. A row here corresponds to a constraint here, and that this should be smaller or equal to 1 is that I'm allowed to have at most one edge that includes that vertex. So this is a pair of primal dual linear programs, and we actually want to have that xy, the xy's and yi's, that those are 0, 1. But we don't have to add it here, and we don't have to add it here because we know that A, we just proved on the previous slide that A is totally unimodular. Meaning we do not need to enforce the integrality constraints to actually get an integral solution. So, but because these are dual programs, and because the matrix is totally unimodular, so I get integer solutions on if I get optimal solutions, then duality tells me that the optimum here, so the minimum vertex cover, has a value equal the optimum here, the maximum matching. So from duality, König's theorem follows immediately. Let's see another application of LP duality, and that is the famous Max-Flow min-cut theorem. So we have here an instance for the flow problem, the maximum flow problem. The question is how much data can we send over local networks. This example comes from another video where I introduced linear programming or showed you examples of simple linear programs. So flow was one of those. So I want to send data from the origin to the destination. I can send over an edge, I can then send at most as much data as its capacity, and I cannot store data at vertices, so the data that goes into a vertex has to be the same as going out, and under these constraints I want to send as much as possible. So I want to determine in which direction should I send data per edge and how much. For this we've seen LP, and that was quite simple. So for every edge we have a variable, xuv, we have a variable, and we require that the flow on that edge is at most the capacity. And we can use these to express, so for every vertex we'll have a constraint which says that inflow equals outflow. And this I can express by the sums of edges that go in equals, or the flow on those equals the sum of flows of outgoing edges. Yeah, so all of these are linear constraints, therefore I can formulate this as a linear program. Yeah, so flow smaller equal capacity, that will look like this. And okay, if we would have working with directly with an oriented network, this would look a bit simpler because we can still pick the orientation. This, I'm saying that XOA can be between -3 and 3. -3 then expresses that the direction would that it would be pointing backwards. But it has to adhere to the capacity 3. And here's another example. So XAD, that's that edge here, and that value has to be between -1 and 1. And then inflow minus outflow means, for instance, here, if I have the edges oriented in this direction, then I get XAD, the flow on this edge, plus the flow XCD should equal XDN. And this also works if I work with negative numbers here. I mean, negative number here would mean that I actually have outflow, but then it also would go with a negative sign into that sum, so that would be fine. And what are we maximizing here? So what we want to maximize is how much flow I can send out, equivalently how much comes in here, but how much I'm going to send out. This is X, and then simply for all of the edges here, XOA plus XOB plus XOC. That is what I'm maximizing. So here you see all of the constraints that we just discussed. And if I solve this linear program, I get a solution. This would be a solution. And I get a flow of 4. Now we're going to prove that the maximum flow is the same as the size of the maximum flow is the same as the size of the minimum cut, and this will follow from duality. For this, we are going to take this linear program and compute its dual, and we are going to see that the dual tells us is formulation of min cut. So for this, we will first formulate this more carefully. We're going to number the vertices 1 to n, and then Cij is the capacity of the edge from vertex I to vertex j, and Xij is the flow that we send on that edge. F, let F be the value of the flow, of the actual flow that we get. So then the linear program looks like that. We want to maximize the flow subject to these constraints. So these are constraints ingoing equals outgoing, and those should be always 0, except if you had the origin or destination, there should be f or minus f. Yeah, so minus f for the destination. And then we also have constraints that tell us that we stay below the capacities, and obviously all of the flows should be non-negative. We can actually relax these constraints, and the linear program will still work. The advantage of this being that we now have this form. We want to maximize f subject to ax smaller equal b, x non-negative. To dualize this, let's first see what is a and x, b, and c. So what are the matrices and what are the vectors involved? So x, we have for every edge a variable, and we also have this variable f corresponding to the total flow. The c, since we have this f here, is simply 1 for that f, and otherwise 0. The matrix A, so for the matrix A, we have, if you think of the constraints that we have for every vertex a constraint, and then having that ingoing equals outgoing, or if you put all on the same side, then it's outgoing minus ingoing equals 0. So we have some edges showing up with a -1 here, some showing up with a 1, and this overall should be 0. So that's up to here. Those are the inflow equals outflow constraints. Now additionally, I here have constraints that simply tell me that I adhere to the capacity. And now I'm saying that x times this should be smaller or equal to Cij. Note that now I'm assuming that the x are non-negative. For this, I'm assuming that I have directed edges. Or if the edges are not directed, I can also simply take 2 copies, one in each direction. And in this way, make sure that my variables are non-negative. This is actually the same as the trick that you would always use. If you have variables that can also be negative, if you want to make sure that they're non-negative, then you introduce 2 variables. And that you could do here, which corresponds to having 2 directed edges, one in one direction, one in the other, if you want to have that. Now, if you look at the columns up here, so the rows corresponded to inflow equals outflow, but the columns now correspond to edges, and up here, an edge will always, there will be one vertex where it starts and one where it ends. So every column of the submatrix up here will contain exactly 1 minus 1 and 1 1 1, because this corresponds to an edge. Let's dualize this. Before I show you the dual, let's briefly look at this setup here. So our variables here were, for one, this f variable, and then variables for each of the edges. So in the dual, I will have these as constraints, so one f constraint, and then a constraint for each of the edges. Here, this maybe is good to point this out. This was somewhat special that we had this -1 1 here in combination with that f, which told us that for the first and last vertex, the inflow minus outflow shouldn't be 0, but f for the origin and minus f for the destination. Then the b vector, I have zeros here. This corresponds to the inflow equals outgo constraints, and Cij for the capacity constraint. And now in the dual, I'm going to transpose A. C and B will switch roles, and the primal variables will become dual constraints, and the dual constraints will become variables. So we will have, so these were variables that correspond, these were constraints corresponding to vertices. So where I have for each vertex a variable in the dual, and these were constraints corresponding to the edges. So also for the edges, I will have variables in the dual. Now let's make this more concrete. So we have our variables. There we have the variables for the vertices, for the edges, and for the variables we had in the primal, in the B, the 0, because so for the vertices we had the B 0. This was the inflow equals outflow. So this B from the primal gives me the coefficients in the dual. So the variables for the vertices don't show up because I have a factor 0. The ones for the edges show up with their capacity. So I get some Cij, Yij here. Now I'm transposing the matrix A. The first row corresponds to the first column in the primal, which was a column corresponding to the variable f, so the flow variable, which we only used to say that out of the origin and into the destination I should have a flow of f, and this, so that's where this -1 and 1 came from. The other rows correspond to columns which correspond to edges, where I have 1 for where the edge, the vertex where the edge starts, and -1 where it ends. And then eventually for the edge itself, there's another 1 back here. So if I look at a specific edge, so let's say I have the edge Ij, then this, the corresponding row, gives me the 1 for u, for the variable ui, the -1 for the variable uj, and then I pick up the edge itself, so that is yij, and this should be larger equal, and this is then 0. Yeah, so only for the first row I have a 1 here. Yeah, so these are my constraints. Now the same LP written more compactly, so we're minimizing sum of Cij, Yij, subject 2, and then for the first row we got this constraint here, minus u1 plus un larger equal 1, and the other ones we also already saw, ui minus uj plus yij should be larger equal 0. And as a linear program, we would ask for these to be non-negative. This is the same as asking for 0, 1 variables, so for restricting them to 0 or 1, because A is totally unimodular. Yeah, so this ILP, the optimum of this ILP is the same as for the linear program if I just ask these to be larger equal 0, because it only makes only 0 value of 0 or 1 would make sense anyway. Now, and if you look at this dual program, this is now actually a way of formulating minimum cut. So how can you see this? So what is this actually saying? This is saying I'm going to label my vertices either 0 or 1 with the following constraints. Because of the first constraint here, we have to have that the destination un is actually 1 and u1 is 0. So I have to label my vertices in a way that the first one is 0, the last one is 1, and so let me label them. So for any edge, the endpoints of that edge may only vary in their label if yij is 1, meaning if I selected yij. stated differently, I try to select a minimum cost set of edges, Yij, such that all remaining edges have both endpoints either 0 or both endpoints either 1. And this is exactly a cut. Let me show you an alternative duality formulation of max-flow min-cut, which again shows the same but with very different linear program. So here we're going to formulate the flow problem quite differently and in the following way. So this is our origin, we call it now Q, destination S, and let P be the set of all paths from the origin to the destination. Those are many, but I'm going to take all of them. And I have a variable for each of those paths. So it's not an LP that you would ever want to write down to actually solve it, but we're just going to use it conceptually. So I have a variable for every path from the origin to the destination. Now I can formulate the max flow problem now as the following. I want to maximize, then sum over, and I'm placing flow on, I can place flow on these paths, and then I want to maximize the overall flow placed. So this is sum of all path, the flow, sum of all the flows over the path, subject to the following constraints. If I look at any edge in my graph and I look at all the flows that go over that edge, through that edge, then their sum has to be at most a capacity and flows should be non-negative. So this is a way of formulating max flow. Again, a bit strange because we have a very large number of variables, but the nice aspect of this is that we get a very natural formulation of min-cut as a dual. Because what is a dual problem now? So the CE end up as coefficients in the objective function. And so let's simply do it. So I now minimize. So here I had for every edge a constraint. So now I have for every edge a variable, ye, and the coefficient is what the b was here. So I want to minimize cost of an edge times the variable of that edge, subject to, and now I'm transposing the matrix here. Previously, I was looking for every edge. I was picking up all the paths that go through that edge. Now the dual, for every path, I'm picking up all of the edges on that path. So I'm summing up ye for all the edges in that path. So that's what happens if I transpose A. And this should be larger equal. So here all the coefficients were 1. So this has to be larger equal 1. And again, ye is larger equal 0. So we had here the smaller equal gives me a smaller equal here. The smaller equal there gives me a larger equal over here. So that is a dual problem, or the dual LP. And this is again min-cut. Because what does that say? For any path from the origin to the destination, at least one of the edges should be selected in my cut. Let me show you one further occurrence of duality. This is a problem that I already discussed in a previous video, shortest path problem. There we saw two LP formulations, and we will now see why there are those two, because those are actually dual to each other. So here was the first one. So we have a graph G, edge weights. We're looking for the shortest path from S to T, and we can formulate this as an ILP. We will have variables for each of the edges, and this essentially means, so we're going to set it to 1 if we're picking that edge for the shortest path, 0 otherwise. So we want to minimize the number of, the cost of the edges picked, subject to, and then this is very similar to flow. We want to have, this is inflow equals outflow for each of the vertices. And we want to have that the sum of the flows going into the destination is 1. And the inflow equals outflow that was for all vertices except for S and T's. And then for T, we say we want to have 1 coming in. And this 1 has to come from somewhere. This will come from S. Yeah, so this is a flow formulation of the shortest path problem. And now we can take the LP relaxation of this problem, and this LP relaxation will actually have a solution where all the variables are either 0 or 1. Why is that the case? So this follows just like in the case of the min-weight perfect matching from the fact that A as the incidence matrix of a directed graph is totally unimodular. Now let's dualize this. So let's first look at the primal. Here we have for variables for the edges. So in the dual we have constraints for the edges. We'll have here constraints for variables, for vertices. So the vertices will be variables in the dual. And if I look at the constraints here, if you look at how an edge shows up, so it shows up positively for the vertices where it goes into, and negatively for those where they come from. So negatively because if I bring it on the other side, I have a minus here. So my dual constraints will be something like, so for an edge UV, I will have a constraint of the type dV minus du, smaller equal, and then the vector in the dual that I have there corresponds to the C vector in the primal, so the WUV. So this will be smaller equal WUV. So the dual program is actually a program that I showed you in a previous video, but I didn't tell you that it was a dual program. So there I just said, okay, we want to have these constraints fulfilled, meaning that the distance, if I interpret dV as a distance to vertex V from S, that the distance to V should be at most the distance to U plus the cost of getting from U to V, so the length of, or the cost of that edge. And then I just put all of those constraints together, say that the distance of S to itself is 0. And now I want to maximize the distance, the dt for, the distance for t. And the reason that I want to maximize is that if I have all of these constraints fulfilled, the d can get at most as large as the shortest path distance. But if I don't maximize, I can actually make all of this 0. But if I maximize, I do actually get the distance itself. If you look at the constraints that we have here, this is the dual to the other program that we just saw. Therefore, from duality, we immediately know that this is indeed a valid formulation of the shortest path problem, and that the optimum here equals the optimum of the linear program that we just saw. And these are all of the applications that I wanted to show you. So we saw Hall theorem, which we proved using König's theorem, and that we proved using duality for bipartite graph. Min-vertex-cover equals max matching. Then we went on to look at the Max-Flow min-cut theorem, and finally the shortest path problem and two formulations being dual to each other. And that's all.